Okay, I have to apologize in advance because I'm sure this is going to happen. Um, my puppy Jimbo, my almost 1-year-old coonhound, is being a bit of a pesky pest today. So I apologize in advance if you hear him being a pest. Um, and if I have to pause this. So far, so good, but we'll see. We're only like 30 seconds in. Or if you hear him chewing on a bone, because that's how I'm trying to distract him. Okay, let's do this. Yes, I am posting this late, and I apologize. I wasn't able to have access to the computer that I normally use for like writing on like I normally do until now. So that's why I'm doing this now. Okay. Without further ado, you're going to need your notebook to take a few notes in, pen or pencil. Do you really need you don't really need a calculator today. You do need your Eureka book and computer or phone. Some electronic device you can access Desmos on, that graphing software that we've been using the last couple days. Ignore this. Okay, we're actually having a short quiz on Wednesday. The end of module project kind of like refresher is going to be when we get back from Christmas break. So here's kind of the plan for this week. I meant to write this down, but obviously I forgot. Today we're going to be doing lesson 17 in module 2. Tomorrow's lesson is going to be lesson 19, which is going to be talking about this fancy word we call correlation, which you may have heard of before. And then Wednesday again, Wednesday is going to be the quiz. Okay. Now, since you're an online student, or absent or quarantined if you're watching this, most likely, just note that since I'm posting this lesson 17 so late in the day, you have through this entire week to get all of this done. So don't feel like you have to rush through like both of these lessons tomorrow and this the next day. Okay, you have the whole week to do these 3 things. It sounds like my dog is chewing something else. Okay, let's do this. We're going to talk about residual plots for a minute. Let's see if I can find my dog while I'm doing this. Oh, good boy, you're just chewing on a ball. Okay. So last time we talked, or I talked at you in this in the video, we made a plot that looked like this. Okay, we were measuring. Let me zoom in a little bit. This, maybe you can recall this. We were looking at shoe length and height of, I believe, 1, 2, I think 10. Oh, 9. No, I think 10, because I think 2 dots were the exact same. 10 adult males. Okay. And we were seeing what kind of relationship it was, meaning, was it linear? Was it exponential? Was it a strong relationship or a weak relationship? Meaning, how scattered was it? How consistent was it? That type of thing. Okay. So this is the scatter plot that we got. Now, we're going to be talking today about those scatter plots, but also a plot that goes with it called the residual plot. Residual plot. Okay. Now, if you remember from the last 2 lessons, I believe we've talked about residuals. Residuals are essentially the prediction error. Okay, so that's what residual means. How you calculate the residual, just as a reminder, you would take your actual y value, so your y data, and you would subtract your predicted y value. And to get the predicted y value is essentially, let me see if I can kind of put this on here. It's essentially the points that are on the line. Sorry, that is not straight. The actual y data, that's not going to show. The actual y data are the actual data that you collect, meaning the dots. Okay. So that's a quick reminder on residuals. So a residual plot then would be when we have, if you look at this plot right here, let's see if we can, the x-axis is still shoe length, okay? We're still looking at shoe length for your x value, but your y value is actually going to be your residual, okay? So essentially what we're doing is, let me see if I can do this. I don't know if I can, but we'll try. Essentially what we're doing is taking this. Nope, that's not what I wanted to do. I don't know if I can actually do this or if it's just going to be, nope. Nope. Okay, basically what we're doing is taking, maybe I can just tilt it with my fingers. Let's do it. Let's try. Okay, we're basically taking that scatter plot line. Nope, it won't tilt for me. I'll just draw it. So we have our data right here. We have our dots. Basically what we're doing is taking that line and turning it like this. Okay, and that gives us our, again, shoe length. So shoe length, that's still the same value. The x is still the same value, but the y now is the residual or the error. Basically the distance between the point and the line. Okay, hopefully that rings a bell. See if I can draw a better picture for you. I'm doing this standing up while I'm walking around monitoring my Jimbo. So, okay. So residual plot is going to look something like this. A very rough sketch of that. So basically it's just telling you how accurate your prediction line was, your line of best fit. Okay, your regression line, your least squares line, whichever one of those you want to call it. Jimbo. Okay. It's tilting on me. Okay. So that's a quick refresher on residuals and kind of an intro into what a residual plot is. Come here, Jim. Come on. Sorry, guys. I know some of you have pets, so hopefully you understand. Okay. Lesson 17. It's just as if we were in class and you guys were getting me off on a tangent on some kind of tangent. Jimbo, come here. Now it's just my dog instead of you guys. Okay. All right, so we have the scatter plot, new data. We're not looking at shoe length and height anymore. We don't know what the variables are. We're just given this random plot. We have an x and y variable, and we're looking at the relationship. Let's first maybe talk about what the relationship would be. Okay, so notice the data are fairly consistent, right? They're pretty close to the line, right? Whoa, what's happening? They're pretty close to the line, right? It doesn't spread too far from the line. There's not points like out here, right? So it's fairly consistent, which means it's, what was that, Jim? Which means it's a pretty strong relationship, okay? We're pretty consistent, less scattered. We know it's according to the line, emphasize that, according to the line of best fit here, or the prediction line, it looks like it's a linear and positive relationship, meaning as x grows, y grows. Okay. But take a second to look at kind of the pattern of the dots compared to the line. Okay. What I mean by that is we've got a cluster of dots down here, cluster of dots up here, and then it's starting to go down here again. So that general pattern, Jimbo is getting into his Christmas present. I'm going to be upset. Jimbo. Come on, bud. You know better than that. Yes, I talk to my dogs. Don't judge me. Or do judge me. I don't really care. Okay. I mean, I care about you. Just not whether you judge me for talking to my dogs. Okay, where were we? Do you disagree, Jim? Okay. So we were looking at the pattern of the dots compared to the line. So kind of what I was saying is that we have this weird kind of arc happening. Okay, I just exaggerated it, but we have dots below, then above, then starting to go below again. That is essentially what our residual plot would look like. Okay, here's the same scatter plot. Here's our residual plot. Okay, again, the residual plot is looking at the error in our data compared to the line of best fit. So these distances here. I'm not going to draw all of them, but you get the gist of it. So if you were to just rotate that line, rotate this line a little down, a little up, so it's straight, that's basically what the residual plot looks like. Okay. And the residual plot is a little bit zoomed in. Okay, Jim, come here. Get your bone. Get your bone. No, not my pen. So this is what our residual plot will look like for this scatter plot. Now, I want you to notice the pattern in the data here, right? There's, on the residual plot, there is that arc happening again. Remember how I exaggerated that arc there? There's the arc happening. I want you guys to think about what that pattern in the residual plot might tell us. Okay, I'm not going to answer this question right away. We're going to look at a few other examples and then circle back to this question. Okay, what would a pattern in a residual plot tell us? Okay, so think about that for a minute. Okay, looking at oh, Jim. Goodness gracious. I don't even know where he gets half the stuff he chews, you guys. It just appears out of nowhere. Okay. Hopefully you're being entertained and not annoyed by my dog. Okay. How about you go outside, Jim? I should just pause this, but it's fine. It's real life, right? Just like you guys distracting me in class. It's all good. Okay. So we have a new scatter plot. This time we're talking about curb weight of a car, meaning what's the weight of the car before you add anything extra to it, like people or luggage and that kind of stuff. And we're seeing how that's related to fuel efficiency of a car, so miles per gallon, basically. The line shown here, this line, was calculated as the line of best fit, so that nice prediction line, right? I want you to think about this question for a second. What kind of residual do you think point A would have, point B would have, and point C would have? Think about that for a minute, and then, so maybe pause, think about it, and then unpause. Okay, looking at this plot, I zoom in a little. Again, residual means the distance between the actual point, this point, and the line of best fit, which is essentially a prediction of what the point would be. Okay. So knowing that little extra bit of information, how would you describe these? Well, I'll tell you what some of your classmates said during class today. They noticed that A and B were both positive residuals, meaning they're above the prediction. C is a negative residual, meaning it's below or smaller than, lesser than the prediction, which is this point right here. They also noticed that C is a lot bigger, right? It's a lot bigger of a distance or error than B and A. Okay, you're like, why does this matter? Well, here is the residual plot for the same information. So here's the plot we were just looking at, and here's the residual plot for that data. So again, you can kind of see how this line, if we were to turn it horizontal, that's basically what our residual plot would look like, right? So here we are looking at point A, the residual for point A, meaning the curb weight in hundreds of pounds for car A was around 2,500. And the error between the actual data point and the predicted point was about 3 miles per gallon. Okay, so that's about 3 miles per gallon error, meaning it was a positive residual and not that big. The residual for point B. Here we have a curb weight of about 2,700, and the error is something like 1/3 of a mile per gallon. So it's really small on this one. 1/3. And then C was the huge error here. That was a really bad squiggly. Okay. So this is point C on the residual plot, matching this point C here. Okay. And what this point on the residual plot is saying is that the car was about 2,800 pounds. Okay, and the prediction error was about -6 miles per gallon. So meaning it was 6 miles per gallon below the predicted amount. Okay, this is the actual, this is the predicted. The actual is about 6 miles per gallon lower than the predicted amount. Okay, and again, you're probably like, why does this matter? I promise you I will answer that question, just not quite yet. We are going to get onto Desmos though and calculate residuals plot. Now this this will get you a residual plot. Do we have to do it this way? No, I'm going to show you how to do it on the computer. Okay, so maybe pause this screen and kind of follow these directions to get your scatter plot going, or come back to this screen. But I am going to walk you through it on Desmos, so you could also just follow me while I'm doing it. But there's the steps if you just want to look at the steps and not listen to me explain it. So Desmos.com, click on the graphing calculator. That little plus sign there, you're going to click it. And then click table. This is where you're going to enter the data. Now the data you're going to use is from lesson 17, example 3. Say it again. Lesson 17, example 3. Okay. So you're going to enter that data. X is your shoe length, Y is your height. So here we're looking at shoe lengths and heights of 12 adult women. Okay, so go ahead and enter that data, and I'll enter it on here as well. $70 for shoe length. Nice. That would be huge. Mm-hmm. Sent my dogs outside. Might as well tell you a story while entering this data. Sent my dogs outside a couple minutes ago, right? Which is why there hasn't been any interruptions for a minute. My dog Jimbo, he's hilarious. Whenever we let him outside and he wants to come back in, he literally knocks on the door. Like, I don't know where he learned that, but he learned it somewhere. He will literally put his paw like on the window and like tap on it, like over and over until we let him in. It's kind of hilarious. He's doing that right now, which is why I thought of it. For entertaining story of the day. I feel like this month, and that was a dumb story. Well, oh well. I think I missed a number. I did. His mom's in. At least we're not too far off here. All right, there's our data. So if you're not caught up with the data, you're probably like way ahead of me. But if you're not caught up, maybe just pause the video. Once you are done entering that data, though, you are going to click on the empty space below the table. So kind of like where I just clicked. And here you're going to type that awesome linear equation. So it's going to be y1 tilde. Let's see if I can remember how to do the tilde on here. I know it was something really obvious. Ooh, well that's fancy. I didn't know that was there. Tilde, where are you, tilde? Yeah, I know, I can't see, it's fine. There it is. Okay. y1 tilde mx1 plus b. So type that in, just like that, okay? Now notice down here, this little thing called residuals. Actually, before we click on that, click on that little wrench button in the top right corner. Okay, I'm going to change this so we can actually see our data. The range for the x variable, the shoe length, is about 8 to 12 maybe, so you could do that. I'm gonna do negative. I like seeing the axes with the graphs, so I'm just going to do -2 up to 15. And then for the y-axis, I'm going to do, looks like it's a range between kind of like 60 to 70-ish. But again, I want to see the axes here, so I'm actually going to do -10. You don't have to do these exact numbers, but you might see why I want to see the axes in a second. To, let's say, 75. Okay, so now, hey, it was automatically Christmas colors. Look at that. And now I'm going to ruin it and do reverse contrast because it's easier for me to see. Okay, you don't have to. It's just easier for me to see. Okay, let's go back down to this little equation thing. See the thing that says residual, and then there's a button that says plot underneath it? You're going to click on that plot button, okay? And you'll notice that a bunch of dots just showed up. I was trying to write. Let's see if it'll let me. A bunch of dots just showed up down here, okay? So here is your actual data, and here are your residuals. So it basically gives you two plots in one. You have your normal scatter plot and your residual plot all on one graph, which is kind of cool because you can see the relationship between the data, but also how accurate the data is. Okay, so how spread out the data is, how much error there was, etc. Okay. So looking at this plot, we can also see, did not mean to do that. We can also see the equation here. Come on. I just want to write again. Oh, wow. That was weird. Okay. See if I can figure this out. Nope. Oh, well, that's fine. We have our data, we have our residuals. Now, I really need to be able to circle something. I'll just show you here. So I'll go back to it, but where that equation is, right here where we clicked on plot, notice there's the M and the B. That's your slope and your y-intercept for the line of best fit. Okay, so there's how we calculate the line of best fit there, the equation for it. Now you can calculate it by hand, but that's really complicated and we're not going to get into it right now. But you see here that the equation for the line of best fit, if you look where that slope and the y-intercept is that I just pointed out, the slope is 3.15 rounded to the nearest hundredth, and the intercept would be 32.68. Okay, so the equation then for this data, this line of best fit, would be y equals 3.15x plus 32.68. I don't know if you can hear my dog's barking, but that's happening right now. Okay. Come here. You're fine. Oh. Oh, my dog's just almost face planted, slipping coming inside because of the snow. Okay. So one thing I want to look at before we move on from this graph is how to interpret the slope here. So the slope again was 3.15. What that would mean in context here is that for every 1 inch, our shoe length increases. So our x variable, wish I could draw again. I can't remember how I did that. For every 1 inch our shoe length increases, so on the x-axis, the height will typically increase by 3.15 inches. Okay, so that's how we would interpret the slope here. Now, the y-intercept really wouldn't make sense to interpret because it would mean a shoe length of 0 inches. And if you have a shoe length of 0 inches, there just isn't a shoe, right? The shoe doesn't exist. So the y-intercept doesn't really make sense to interpret in this particular situation. Okay. Let's move on. Whoa there. Okay. So one thing I wanted to point out, and this circles back to the question of what do you think the residual plot is telling us if there's a pattern versus not a pattern, right? We saw that arc in the scatter plot earlier. Okay. This is a really important thing to remember. So I would maybe write this down, this highlighted part. at least. So in residual plots, and there should be an N there. Forgot to add that after class today. In residual plots, if there is a pattern, so if you're looking at your residual plot and you see a like arc, kind of like we did on that first one that we glanced at earlier today. Let's see if I can actually just get back to that so you can remember what I'm talking about. There we go. See that arc? Okay. If there's a pattern like that in your residual plot, so not your scatter plot, the residual plot, it means that the line of best fit, so if we chose a linear equation, for example, it means it's not a good fit. Okay. It could just be a really weak relationship. Most of the time, though, it means that if you chose a linear line of best fit, it means your data is actually nonlinear. Okay, so let me show you what I mean by that. Jimbo, stop. Actually, I don't need to go anywhere else. I can just use this. Let's look at these plots. Okay, here we have a linear line. Let me highlight. We have a linear line. The residual plot for that, okay, is this one right here. Okay. Now, before I kind of explain that, take a look at this plot. We have an exponential curve, right? It's increasing at a decreasing rate. And the residual plot for that is right here. Now, notice that these are actually the exact same data. We just use a linear line for one of them and an exponential line for the other. Now, the residual plots look different because here our prediction line was linear, but our data is not linear. Our data was more exponential. So on the exponential residual plot, it looks scattered. Okay. So this is what it means when, if there's not a pattern, it's good. It means it's a good fit, meaning here we had an exponential relationship. So our residual plot looked kind of scattered and random, okay, but still fairly close to the line. Whereas here, our data was the same. It was still that exponential data, but our prediction line, we thought that it was linear, and the residual plot shows that it's not a linear relationship, okay? So that's what I mean by if there's no pattern, whatever model you chose, linear or exponential, was a good fit. If there is a pattern in your residual plot, it means whatever model you chose, linear or exponential, was a bad fit. Okay, which is kind of what this flow chart over here is showing. Okay, so if there's no pattern in your residual plot, it's an appropriate model. If there's small residuals in that, it's a really good fit. If there's large residuals, so if we look at this one again, if the dots were like super far apart, but still random, it means it is an exponential relationship, but it's a really, really weak one, so it's not very useful. On the other hand, if there's a clear pattern, so you have a curve of some kind in your residual plot, okay, maybe it's a squiggly or something, some kind of pattern, it means that whatever model you chose, so let's say you chose a linear model for data that was actually exponential, it means it was the wrong model. Okay. All right. This bottom plot here is a really good example of an appropriate model that's not very helpful. Okay. So you'll notice that the data over here look linear. So they used a linear line to predict, right? They used a line of best fit that was linear. And the residual plot looks good. Like it looks random. There's no clear pattern here, right? So that part of it looks good, but you'll notice that the dots are a lot more spread out than, say, this one was, right? So that means it is a linear relationship, but it's not a very strong one. Okay, so that's a good example of that. Okay, so think about this. Maybe pause it if you need to think for a longer time. Is a linear line a good fit for this data? What do you think? Would a linear line predict this data really well? And you can look at the residual plot to kind of help you answer this. Okay. So let's walk through this. You'll notice that the data does look pretty linear, right? That was not a straight line. The data does look pretty linear there, something like that. But when we zoom in on the residual plot, what's happening? There's a very clear arc happening, which means that the data was actually not linear. Okay, and you can actually kind of see that. You can see how it's kind of dipping over on this end, goes up here, and then dips again, right? Kind of like that first scatter plot we looked at. So this would be a no-go. A linear line would not be a good fit for this data. It would be, it's actually what we would call quadratic. But the point is it's nonlinear. How about this one? Think about this one. Here we have our data. Here we have our data. Would a linear line be a good fit? So if we put a linear line through there, this is what our residual plot would look like. So is a linear line a good fit? Well, it should be pretty clear, right? There is a giant arc, and it's even more precise and obvious than the last one, right? So a linear fit here would not be a good fit. Okay, how about this one? Let's check out this one. So here we have our data, and it's asking, is a linear line a good fit for this data? So if we had that linear line there, this is what the residual plot would look like. Do you think it's a good fit? Okay. Now on this one does look random on the residual plot. So a linear line is a good fit. So my follow-up question would be, is it a strong relationship? And the answer would be, it looks pretty moderate, right? It's not super weak, it's not super strong. If it was stronger, the residual points, so the data points would be closer to the line, kind of like this, okay, rather than farther spread apart. But it could be worse. It could be a lot more spread apart, right? So it's definitely random, which is good. It means it's a linear fit, but it's a moderate or a weaker relationship than it could be. Okay? Okay, that's it for today. There's no other work that you need to do. That being said, if you do want to kind of practice on a problem on your own, a really good one that asks you like to plot some data and then look at the residual plots. And again, you don't need to do this, but it's there if you want some practice with this, would be lesson 18, and it's exercises, sorry, Jim, exercises 1 through 3. So it gives you some new data that you can plot. You can practice plotting, finding the residual plot, and kind of interpreting it. Okay. But again, you don't need to do it. You don't need to turn it in. It's just if you want some practice with it. Okay. So that's that for today. Just kind of talking about residuals and how to interpret a residual plot, what it means. And this is actually lesson 18, exercise 1 through 3, is actually a really good example about why we even should look at residual plots. And let me talk about that for a second. I don't remember exactly what the scatter plot looks like, but they fit a linear line to it. Okay. And it might actually be negative. I can't remember. But the point is, they have a linear line fitted to some data. And then their residual plot, the residual plot, when you plot it on the scatter plot, actually looks like the dots are, that was a really bad representation of it. From zoomed out, the dots look like they're basically on the line. But when you zoom in on the residual plot, if you do this, you can see that there's actually a very clear pattern, which means your data is actually exponential. Again, I can't remember if the data is decreasing or increasing, but you get the gist of it. So that one's definitely a really good example to look at for why even look at residual plots. Because again, sometimes our data looks linear and it's not. Kind of like on this one here, right? Sometimes it looks linear. Sometimes it looks linear, but it's not, okay? Which is why it's always a good thing to look at your error, your residuals. All right, again, that's it for today. Let me know if you have any questions.